SeeSAR, which we named Narcissus. And there were two big changes. On the one hand, we have this beautiful new table, molecule table, tables around all modes for convenient compound management. I think we can discuss it directly within SeeSAR. And obviously, we have introduced a new mode, namely the Similarity Scanner, which opens up the world of ligand-based drug discovery in SeeSAR itself. Before we maybe start with ligand-based drug discovery, maybe to address some scenarios where ligand-based drug discovery might become attractive for you. Obviously, sometimes you have to rely on ligand-based drug discovery if there are no target structures available. So this includes also things where you don't have a possibility to construct a homology model or no AlphaFold structures available. So every time there is no concept of generating something as a model or true 3D coordinates of a target structure, you have to rely on ligand-based drug discovery if you want to push your project further in the direction of lead compound evolution or lead generation. Secondly, there are some cases where you have a target structure available, but it's very challenging to handle. So very flexible structures like GPCRs or transporter proteins or membrane-bound proteins are very difficult structures to model. This is true for SeeSAR. This is also true for other software out there that may perform induced fit docking or induced fit binding site prediction, binding mode prediction, because the high flexibility is taken into account within within induced fit docking, but only to a certain degree. So huge conformational changes upon ligand binding cannot be covered by simple docking methods and have to rely on more on methods that require more computational effort, like MD simulations, molecular dynamic simulations. The third point is pretty interesting. Sometimes the target is not even known. So if you have, like, I don't know, cancer cells, and you just have many cancer cells from many different origins here and there, and you take your compound library and you sprinkle all your compounds and all the cancer cells and take a look at them after some incubation time, and you expect and you expect cancer cells to die, and you see, okay, compound 94 led to a reduction in cancer cell activity in 5 different cell lines, so it's likely an anti-cancer drug. But you don't know where it binds, how it binds, and so on. So sometimes not even the target is known. So it's also true for antibiotics, especially, or antivirals per se. Fourth point is it's not a trivial one. Sometimes the binding mode of compounds is unclear. This is especially true for compounds that may have several binding sites, like fragments. This is also true for compounds that have an initial binding site and then approach the primary or the important binding site after the first binding event of the distant binding site. So also something where ligand-based drug discovery can be a huge benefit to the project. The fifth, structure-based approaches lead to not satisfying results. Obviously, sometimes you just try to model things, you try to dock things, and things just don't work out. There is no SAR that you can dilute from your research, from your findings, and sometimes it's just a dead end. You try everything, you try ritual screening based on a binding site prediction, and everything just fails because obviously the binding site is not that well conserved, or there are some other challenges, there are some conformational changes that you did not predict. And this is where structure-based drug discovery also may reach a limit, where ligand-based drug discovery may another approach to which can lead to better results. Sixth one is scaffold hopping. So you can obviously try to perform scaffold hopping based on fuzzy pharmacophores, on other techniques where you try to clip here and there and replace a core pharmacophore with something familiar. But this is also where ligand-based drug discovery may be very interesting, because you are removing that limit, I would say, of the binding site and try to think a little bit outside the box. We just say, okay, I just want to have this shape in place, and I don't care about the binding site information at this point, and just try to perform a ligand-based drug discovery approach. So also very interesting for scaffold hopping. The seventh one is not standalone. feature of ligand-based drug discovery, namely the enrichment of hits. Ligand-based drug discovery can also be very useful if you have already performed some sort of pre-filtering, like QSAR or docking results, or I don't know, whatever you find interesting, and you have a list of compounds, and you just want to enrich hits. So you want to have the hits to be the hits more success, to have a more successful hit rate with a subsequent addition of a second filtering step. This second filtering step can be ligand-based drug discovery. Just maybe a little bit more obvious, a pharmacophore generation approach, where you try to deduct information based on known actives, where you don't know how they bind, maybe because there's no target structure available or something like that, and you try to have two different scaffolds aligning, and from this perspective start the pharmacophore generation idea. So okay, you can see that there's an H bond there, there is an H bond donor there is an H bond acceptor on the other place, there's a phenyl ring there, and based on that you can construct a pharmacophore for other subsequent screenings. So now to the Similarity Scanner Mode in SeeSAR. The two main challenges of ligand-based drug discovery are mainly the generation of conformations. So how does a molecule in 3D look like? And how does a reference molecule look like in 3D? And the second challenge is actually to find a similarity between both of those. So if you have conformers of molecules, how can you align those where there is a similarity or there is a reasoning behind it, how they superpose the best way or align the best way? This is where the FlexS algorithm kicks in. This is a little nice graphic I have added. I think I've messed up the colors here and there, but nevertheless, I think it's still understandable. I just get a pointer. So what FlexS does is, FlexS is not an algorithm that just aligns heavy atoms above each other. It heavily uses the matching of H-bonding partners in both molecules, yet the interacting atoms are not used as a main driving force for the superpositioning. So what basically happens is you have a nitrogen atom somewhere, and FlexS goes here and says, okay, this is an H-bond acceptor. And it defines the perfect H-bond angle for this nitrogen, and also not so perfect H-bond angles in other directions. And it generates a grid based off triangles. So you have an atom. This atom has some interaction properties, and SeeSAR calculates perfect matches for an interaction partner in triangle shape. And it does it so for all H-bond acceptors. The H-bond acceptors was correct. It also does the same for H-bond donors. And it does the same also with lipophilic groups and moieties. Now I've spared you with a triangle matching, but you can imagine that this methyl group has also lipophilic interaction partners. Same goes for this trifluoro methyl group below, and so on. Ethyl group, also aromatic groups from the phenyl ring, from the pyrimidine ring here and there. So why is this important? What FlexS, the algorithm behind the similarity mode, it generates a pseudo receptor, a pseudo interaction point receptor based on a ligand shape. So we do not search with FlexS for perfect matching of substructures or specific atom groups, but we try to find something that fulfills the perfect arrangement of molecular features within a 3D space. Something fairly unique because it does it very, very fast, and you do not need an additional step of conformer generation in the initial step. So normally you need to generate a huge set of conformers and then use one conformer of your test molecule and then try to align all the other conformers based on your test molecule reference conformer. We do not need that. We don't need huge libraries of several gigabytes of conformers. We can do everything we want to do within SeeSAR within minutes or seconds, depending on the size of your library. Without further ado, I would love to close this window actually. That's closed. And I will now start with a project. So the things you will notice when you open up SeeSAR, you end up like this. I hope everyone is more or less d'accord with the dark interface I use. Some people like the light interface, but I'm more of the dark type. Now, if you hover over the mode selector, you will notice there are some of the more prominent modes of SeeSAR, like the target editing sector of proteins binding site and protein editor, the molecule structure-based set of analyzer molecule editor mode, inspirator mode, and docking mode. And now we have introduced the ligand-based drug discovery world with the Similarity Scanner on the right side. So let's click on the Similarity Scanner. And my deductive perspective is actually to show you some examples, what you can do with SeeSAR. I will start with a simple operation. So once we are inside the Similarity Scanner, we now have the Similarity Scanner open and it asks us to please load molecules. You can do that by going to your SeeSAR menu in the left top corner, go to load molecules and select any STF file of your preference. But what you can do as well is just open up a SMILES string. I will use this string of carboxylic anhydrase inhibitors. And with simple Control-C, Control-V, I can paste all these molecules. And from the SMILES strings, all molecules are generated instantly. Here we're working with dozolamide, an FDA-approved drug. And I have added another set of 3 compounds, just a set that was all published based on FlexS. And this is my reference compound. This is what I want to use as a reference for the alignment of the subsequent molecules, ligands. And these are my query ligands. So what I want to try, or what I want to do, I want to align compound 1, 2, and 3 on dozolamide. To do this, I have to select a template molecule. For this, I will go to dozolamide, and I have to click here. As you can see, once I hover over this beautiful button, a message pops up, and it asks me if I want to set this molecule as template molecule. Please, yes. I will click on it. And now I have some options that I can do. I can adjust the parameters. I can tell SeeSAR how many, what's the maximum number of poses per molecule that I want to generate, and also the minimum similarity rating. A similarity rating of 1, represented by 5 hotel stars. A similarity rating of 1 tells me that both molecules align perfectly. This can happen for obvious the same molecule, but molecules that are very close, although not from a Tanimoto-based similarity, but from a shape-based similarity, can also come close to this 1.0. 4 stars are actually fairly interesting if you want to have pretty good results for visual screening. So this would be actually my suggestion. If you have a STF file of, I don't know, 10,000 molecules, or maybe 5,000 molecules, and you want to see which compound may be similar to your reference compound, I would suggest to give you like 4 stars to have really, really good superposition and alignment of molecules. So very good for a similarity scan, for a visual screening approach of ligands. And if you want just to play around a little bit and to see what happens here and there, 0.6 is the perfect similarity score for you. So basically the standard setting is pretty fine to do everything you want to do. We can also apply Pharmacophore constraints, but I will do this later on. I can even do it right now, actually. Maybe let's start with Similarity Scanner first. So once I have adjusted the maximum number of poses I want to have, and also adjust some similarity rating, I can just simply click on my play button, and the poses will be generated. So that's it. 3 were generated within, I don't know, 10 seconds, 15 seconds, I think pretty fast. And this is where you get your results. If you want to align your results based on the similarity rating, you can do it by clicking on the similarity rating column here. And the best results will pop up on the top if the arrow shows down. So results on the bottom have a decreased rating. What's new? Maybe you have noticed that we changed the outlay of the tables, as I've mentioned. So there are now nice additions to the system, to SeeSAR. This is now the compound that we have aligned. And if you want to compare this compound to our initial compound, or our reference compound, we can click on here on this pin, which keeps the molecule visible in 3D. Et voila. Intozolamide in green, and our test query compound now in beige in an overlay. And you can see this is the predicted alignment of both. You can also again click through the poses and check how well they compare. Maybe there's something you like better. And this is the only generated pose with 3 stars for the compound number 1. So you can either click with your mouse wheel, or you can use the arrows to select the compounds you want. If you do not like green, you can click on this watercolor palette or color palette, artist palette, and select the color of your preferences. So if you're more of an fuchsia type or more of an, I don't know, marine blue, it's not marine blue, but it's blue, you can adjust the colors every time. And again, if you want to keep a certain position compared again with others, click on the pin and it will be kept visible in 3D further on. Another new addition that we have added to the table update is actually the possibility to mark your compounds as active with a flame or inactive with a snowflake. And you can also rank your compounds based on the additions you made here and there. If you want to give a compound an annotation, you can do that. No problems. You can also mark your compounds as highlights, and you can also, again, every time rank those compounds based on the properties that you gave them. This is the new table outlay. It may look a little bit more, it may look a little bit unsurprising and not so flashy, but once you use it, you will notice how amazing it actually is and how fast it is compared to other software out there. Now back to the Similarity Scanner. Maybe I will give you some ideas of how it works, namely with the Pharmacophore constraints. The biggest feature of Pharmacophore constraints is actually to understand how to place those so that you can augment your results and also enrich your hit compounds. So we have a huge selection of Pharmacophore constraints that you can apply. And for the Similarity Scanner, I think the both most important are actually the acceptor interaction contact and the donor interaction contact. So if you take a look in this nitrogen here, at this nitrogen here, the nitrogen of the sulfonamide, if I now click on this nitrogen, I can ask the SeeSAR to show me perfect angles for interaction partners. So based on this nitrogen, it will realize, okay, I can have either an H-bond acceptor here and here, or an H-bond donor here. Obviously, it can turn around. It's not the case for other for other atoms like this oxygen here. And if you now click on this interaction point, which is the perfect distance for an H-bond partner for this hydrogen of the nitrogen, you can set this here to this point, make it be a little bit lower, and ask SeeSAR, hey, place something that is an acceptor interaction contact, and apply. So now, in this position, SeeSAR will look for ligand superpositions that have the exact same interaction point as this nitrogen. So it doesn't have to be a nitrogen, it can be even like an hydroxy group or another H-bond donor. And SeeSAR will also try to align those compounds based on your pharmacophore constraints. So very useful, and we can also try it here and there in the next examples. Again, you can define other constraints if you feel like, hey, I want to have, I want to use, you can also move the constraints with your mouse. I want to have a phenyl or an aromatic group in this tyrosine region, place it there and tell them, hey, I want something aromatic there, select aromatic, select the radius you want, and apply. So SeeSAR will superpose molecules and place all those aromatic regions in your pharmacophore constraint region. That's it. This is how you operate the Similarity Scanner Mode. Maybe you've noticed, so I want just to lose one comment. If you click here, if something went wrong, SeeSAR tells you in the section below, here in the bottom right corner, with an exclamation mark and an alarming red that something went wrong. And if you click on it, it will tell you one of the compounds, one of the three molecules were not superposed. And in this case, it was compound 3. So now I will just spoil you the story so you don't need to read the publication yourself. Compounds 1 and 2 were active. Compound 3 was not. It's just a retrospective story, so please do not take it as a selling argument from my side or an introduction argument from my side. But I have prepared very nice examples for you to understand the concept of the similarity scanner. We can also show you how well it performs even in predicting X-ray crystal structures. So let me quickly check if there were any questions so far that I have to answer urgently. So the question is if it works for thousands or thousands of compounds. Theoretically, yes. SeeSAR is able to handle up to 50,000 molecules in one session. So if you have now the Similarity Scanner Mode, all the compounds of this window, so all the molecules that you have loaded in, and all those generated poses all together have to be a maximum of 50,000. You can kind of like circumvent that if you load 1,000 molecules here and generate 1,000 molecules here and generate 500 poses per molecule. You would obviously reach a limit of SeeSAR. But if you just go at 400 poses, you would have 40,000 poses plus 1,000 poses. So therefore, you could just make smaller sessions where you screen a smaller batch of molecules each time. But Flex S per se is also available as a standalone command line tool. So if you really want to go this way and do everything in command line, it's also possible with Flex S as a command line tool. The other questions are a little bit more demanding, so I will just continue and answer them at the end, towards the end. Next one, example 3. So this example is just to understand how well, or the strength of the Similarity Scanner Mode. As I can see, to move this window. Oh. So this is the template compound I've used. It's actually GPCR. It's namely the S1P2 antagonist, a candidate for the treatment of idiopathic pulmonary fibrosis. And what I did here is actually just preparing an example of SeeSAR's alignment. And in yellow, we have our candidate, our reference compound. And in blue, we have our alignment. So if you just, let's do it like this. It doesn't work. Like this. So this is the proposition of both. And you ask yourself, well, where's the beauty? Where's the surprise? Where's the fun? So on the left side, not very surprising, not too much. The trifluorometry group aligns pretty well. Obviously, it's very hard to align both etoxy chains, both ethers, because they're not in the meta and ortho position, so there's a big difference. But if you take a closer look here, it becomes more interesting, because the whole part on the right side, after the urea moiety here, so everything that is now here, is completely different to what we have here. As you can see, in our initial compound, we have a 6-membered ring, while in the next compound, we have a 5-membered ring. This 5-membered ring, we have the placement of both nitrogens in the same orientation, I would say. But what's really interesting, through this point modification, we can see that we do not lose any lipophilicity. Sorry, we do not lose any lipophilicity in this position, but we have kind of like a scaffold topping approach, where we still can reach with an ethyl group this methyl alignment here. Furthermore, not only this both hydrogen bond acceptors, but in the terminal aromatic group, we can see this pyrazole, and this furan ring. And you ask yourself, well, where's the similarity? In this case, this nitrogen, which can act as a hydrogen bond acceptor, has the same qualities as this oxygen that can also act as a hydrogen bond acceptor. So the whole alignment may be a little bit trivial, but if you would take a look at the 2D structure of both compounds, let's even go to a grid. So if you have this alignment of both compounds as you have them now here, you see that they're not obviously similar, at least on the left side. Especially if you take a look at the right side, you have an urea, which has some, I wouldn't say nasty properties, but they sometimes have solubility issues. I don't think that is true for this compound because it has too many nitrogens in the aromatic rings, but nevertheless, it can be a problem. And by doing this similarity scanner method, you still manage to have a scaffold hopping on the left side and find something that may be of interest to you, especially since you also lose this nitrogen of the urea moiety, and therefore maybe even improve the solubility of the compound. And once again, this is just based on a similarity scanner approach. This is ligand-based drug discovery, so you can do something like this on your own with just your active ligand. Yeah, so what you need for a ligand-based drug discovery approach is just a known binder or an active ligand, and that's it. You need just the smile strings, and then you can go ahead and do whatever you want with it. Next one is example number 1, from my list at least. So what I did here is now a bit of interest, is a little bit more interesting to you. I have loaded anti-malarial drug, which was published, I don't know, 2 months ago, and did an infinity search with it. Maybe a quick look at the infinity search itself. This was my my reference compound, my anti-malaria drug, and what I did, I loaded it into SeeSAR. Maybe for the guys who are not familiar with SeeSAR, therefore you will most likely not be familiar with Infinity as well. Infinity is our second drug discovery platform, and it's used for fuzzy pharmacophore searching within vast chemical spaces. So we have chemical spaces up to the size of 10 power 11, so billions of compounds, of accessible compounds, and we perform an F-trees searching approach. So we search for fuzzy pharmacophore similar compounds within those spaces that can be also synthesized with more or less robust chemistry. So you get a lot of results here and there. And once you click the results, you have obviously no idea which one of those are of greatest interest to you and which are more likely to be active or not. So what you can do once you have this kind of search where you don't know, is this really the good thing, because F-trees is very agnostic to stereochemistry, you can use the results from Infinity and load them into SeeSAR and perform an enrichment screening. So you just load all your results, all your 217 compounds from how many? Actually, it should be calculated. How many compounds we've screened? 20 billion, 30 billion, approximately 35 billion. 35 billion compounds, and we've discovered 217 close analogs to that. And after doing that, we aligned those and got some ideas and results. So now I will just switch over to the analyzer mode where I have stored the results. This was my initial hit compound in yellow. I will now quickly switch a little bit so it becomes more evident. And if you now take a look at the results, we can now see how well those actually align. So again, here, this nitrogen in this position aligns pretty well with those nitrogen, with the nitrogen in this position. The oxygen of the carbonyl group in close proximity to the other oxygen. On the right side, it tries to align the morpholine ring. In the scaffold, second one, we can see beautifully how we also have a scaffold hopping approach. Now we cannot tell for sure if it's from the affinity search or if it's from the similarity scanner per se, but you can see on the right side, perfect alignment. Nice idea for another pharmacophore core in the middle. Now this time it's a triazole. You can still see that those halogens have a very similar orientation, pretty similar binding site orientation. What's also pretty interesting, in this case, it tries to align those oxygen, and I would not be so sure if I could tell if it's based on this carbonyl oxygen or if it tries to simulate those H-bond donator nitrogen here. And in the last compound, again, a little bit of a scaffold hopping approach. We downsized the 6-membered ring down to a 5-membered ring. And here in this case, it tries to simulate this morpholine ring, or tries to align those morpholine ring to this amide here, and also here the nitrogen in the north of the alignment. So this is basically, I think we all have more or less now a good concept of how to use the similarity scanner as an enrichment method for ligand discovery. I also have a third and fourth example. I'll just maybe downsize it to the fourth example because time is progressing faster than I expected, to be honest. Let's go with 4. So this was published month ago or so, on a beautiful adenosine receptor antagonist. From my perspective, beautiful chemistry, very simplistic, but still, nevertheless, very nice core. Again, what I did, I have loaded this antagonist into Infinity. Maybe let's go through the results. Nope, 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 nope. Yes. I got some results and I wanted to use the Similarity Scanner as an enrichment factor. I have loaded all those found similar compounds, 313, with increased or demanded increased chemical diversity, and have aligned those, and then just quick through results after ranking those compounds. And these are just some examples. So again, in yellow, the reference ligand I've used. And you can see that now things become very interesting. A lot of scaffold hopping, a lot of alignment. Again, here it tries to fit hydrogen bond acceptors and donators in close proximity. So you just have to imagine a pseudo receptor around your reference compound that is used as a mold for the conformal generation of your ligands. Maybe a special side story, I wouldn't say side story, but an interesting fact. Since we also have the torsion coloring, you can turn it on for the moment. And you will see that SeeSAR tries to generate conformers based on histograms. So this is empirical. We use true crystallographic data to predict bond angles and torsions. If you use the L key on your keyboard in SeeSAR, you can every time just label those torsions to check if those are good torsions or bad torsions. So this torsion is not so good, at least according to my understanding. 17% is fine, but could be better. This torsion is completely fine. And this is what you can use to, this is what enhances the speed of the alignment. You do not have to particularly go into every single ligand and generate conformers for those ligands, but you can just put everything you have just with smiles, and the conformers that will be generated are also very likely to be, or they are demanded to include only good torsions. So your ligands are very, very good conformers that are generated. Back on track. You may also kind of like expect SeeSAR to obviously include also not only the H-bond donors and acceptors, which are the main driving force, but it also tries to compensate lipophilic interaction points. So it's not that we are using the flex S to predict aromatic centers. It's like just a small part, but flex S tries to predict a lipophilic area around something. So this is also places of areas where you are likely to have a scaffold hopping from a phenyl ring to something like a cyclohexene, maybe, or a cyclohexyl group. So aromatic is not the main driving force, but lipophilicity is. And as you can see here, this is also very interesting. So sometimes you have like those orientations where SeeSAR also tries to match meta and para nitrogens to match each other, because this is most likely also the driving force also for an active compound. It loses a bit of geometry here and there, but it can differentiate between very important interaction points and not so important interaction points. And again, as you can see, at least according to my understanding, a very nice Pharmacophore hopping approach where you almost remove this connecting ring, this thiazole, isotiazole, no, it's thiazole, sorry, and substitute for this indole group on the right side. Okay, before I go over to X-ray crystal structures, let me quickly check if there is anything that I need to answer urgently. So the question is, how big is the library that we can load into SeeSAR? As again, I've mentioned, by the end of the day, the maximum of both windows here and here, so this number added to this number, cannot be above 50,000, but this is something you can adjust yourself, because if you just load 10,000 molecules and you just generate four poses of those 10,000, you can also screen 10,000 of molecules within one session. Yeah. If you just, if you have like 100 molecules and you load 100 molecules and generate 500 poses of them, you will have 100 molecules plus 100 times 500, so 50,000, and this wouldn't work out. But SeeSAR then tells you, hey, this is not working out because too many compounds. FlexS in NIME is still working, so much to that. Yes, the question is if I can show you how to perform normal docking processes. Absolutely. I will do it after the next section. So the other question is if there's a way to lose the data, the similarity rating from the similarity scanner. So far, there is no possibility to transfer the similarity score to the analyzer, because the analyzer works with the affinity prediction. So we have now two scores competing. We're working on a solution to kind of like compensate for that. But what is still possible, if you have your solutions in the similarity scanner, you can check all solutions and then save your solutions as SDF file wherever you want to. And within the SDF file, you would also get the similarity rating as a numerical value. So you can use it afterwards. You can even then include it in the analyzer mode, and it will be also featured as a column within the analyzer mode. Okay, I think the other questions are a little bit more exciting. So I will now just switch over to 3 examples of X-ray crystallography. Give you an idea how well it performs. PPR gamma. So maybe one of the most prominent targets in the past few decades because of diabetes. PPR gamma. One FDA-approved drug as an X-ray, rosiglutazone. You can see it here in beautiful yellow. And I've used rosiglutazone as a template and added this compound just based from SMILES, right? I've tried it also with just rosiglutazone as a SMILES string and added also this compound and performed a similarity scanner, similarity scanner screening. And this is the first result I got from the similarity scanner. Yeah, so in now yellow, our reference compound, and now in our used blue, the result from the similarity scanner. So you would think, yeah, well, I don't know. There's like an aromatic ring in the middle, seems fine. There's something aromatic going on the right side, but it doesn't feel completely right. And what do I have else? Yeah, well, I have like this ring system on the left side that is now a carboxylic acid. And you ask yourself, well, yeah, I don't know. At least I don't have the feeling they are at least somewhat related, or I wouldn't have guessed. So, right, so at least according to my understanding, those molecules are not related in any way if you look at them in 2D. Nevertheless, the similarity scanner told me, hey, they have a very, very good similarity scanner of 4.5 total stars. And now, if we transfer the first initial hit of rosiglutazone, of this compound, I have now used this one and transferred it directly into the binding site of rosiglutazone You can see alignment is still the same. Now maybe switch off the secondary structure. This is the exact same alignment as from the Similarity Scanner. Still the carboxylic acid on this left side. And this one is, as you can see, hopefully, this is the X-ray structure, and this is the Similarity Scanner prediction. X-ray crystal structure, Similarity Scanner prediction. I will now just add both. And you see, not so bad. The carboxylic acid in the same position. I think it's a little bit, it's very close to 2 angstrom RMSD. I haven't calculated it, I'll be honest. But if you just compare a similarity scanner alignment with an X-ray, true X-ray crystallographic data, I think this is pretty neat actually. So this is the first example. I'll now switch over to the next example, NMPET. So this was my template molecule, as you can see on the right side. Not very exciting. Thiourea, pyridine, sulfonamide, and another group. This is the result from my similarity scanner. So maybe again, remove the secondary structure. I wouldn't say that those are per se related. You can see that this sulfoxide here was placed in the same orientation as the sulfoxide of the sulfonamide in the template compound. What's really interesting, this thiourea is kind of like mimicked through this nitrogen here, and it's now a little bit bridged, but the oxygen is very close to the sulfur atom, and the second nitrogen is again back in place. So it kind of like mimics a little bit this urea behavior here and there. And now obviously the question, how well does the prediction of the similarity scanner perform with the X-ray crystal structure? Oops. And again, not perfect, but for just a ligand-based approach, very, very, very interesting. I think it's a little bit low. Yeah, it's very close to 2 angstrom. But again, this is just based on the alignment on a reference ligand. No target information there actually. Again, you can always ask yourself, yeah, well, you had an X-ray structure as a template. So therefore, you know how the coordination of those groups within the atom actually is. And I have to confirm that I've tried it with just the SMILE string. So I've just went to the internet, got the SMILE string, loaded it into Similarity Scanner Mode, and aligned everything just based on SMILEs, and it still works out pretty well. So even the rating is very, very reasonable. So you don't even have to rely on an X-ray crystal structure. Yet I would recommend it to you because obviously if there's beneficial information behind it, why not use it? So use the X-ray if there's one available, but if no X-ray is available, you can still use the similarity scanner because again, every time SeeSAR generates a conformer of a compound, it tries to use reliable torsions. Like in this case, it's even not like a very bad torsion, very uncommon, only 11%, but it's still an X-ray, we don't lie. But in our similarity scanner, the angles are a little bit better. So the torsions are reasonable. In the X-ray again, we have like 2 orange torsions that are also even not very reasonable, 7%. So sometimes even the X-ray is not perfect. And my last example, a glucocorticoid receptor. Again, the story is the same. I used an X-ray crystal structure as a reference. I also did it with smiles, works as well. So this was my reference ligand, reference compound. This is the result from the similarity scanner, and you would think, poof, whoop, interesting. Also, this is something where normal docking would not find a good solution, because you would have a clash in this binding site, as you can see, because the binding site is defined on the surface of the receptor. On the left side, you have the phenyl ring, phenyl group. And after the similarity scanner, now the comparison with the X-ray, close to 1 angstrom. So, I don't know if I have convinced you. If I did not, the best way is to just download SeeSAR and do it yourself to convince yourself. That's why I can tell you everything in the world. I can lie to you. I can just be very honest with you. I can underline everything. I think you have to test it out to believe how well it performs in certain locations. It's not perfect. Nothing is perfect, but it can deliver you very interesting results if you play around with it a little bit. Okay, so this is the main introduction to SeeSAR 12